Ions can be incredibly useful tools to researchers in many different fields. With the right equipment, they can be arranged into beams, accelerated to around 10% of the speed of light and focused down to widths 100 times smaller than that of a human hair. When fired at a sample, these ion beams can trigger a diverse array of physical effects, including X-ray emissions, reactions with atomic nuclei, and the freeing up of new ions. By observing the characteristics of these effects, scientists can learn a lot about the materials contained within the samples they need to analyze. The technology is now so advanced that its uses can range from investigations of centuries-old artwork to analysis of microscopic meteorites. To create ion beams, researchers must first heat gases to extremely high temperatures, creating a soup of hot, charged particles called plasma. This plasma is then accelerated by a strong electric field and focused into straight, narrow beams by specialized guides. Finally, it's fired into a sample where a wide variety of characteristic interactions can take place. By collecting these particles created in these processes and measuring their energies, researchers can make many new discoveries about the compositions of their samples. Known as ion beam analysis, this approach encompasses a wide variety of techniques. One of the most widely used techniques is called Particle-Induced X-ray Emission, or PIXI. Here, the ion beam knocks away an electron in some of the sample's constituent atoms, so that another electron orbiting further out will jump to fill its place. As it jumps, this electron produces an X-ray photon, whose energy is highly specific to the element it originated from. By capturing these photons and measuring their energies, researchers can accurately determine a sample's composition. The technique is sensitive enough to detect just a few atoms of one element out of millions. In another technique, named Rutherford backscattering, a small proportion of the primary ion beam bounces back from the sample. By measuring the energy of these backscattered particles, researchers can determine which atoms were responsible for scattering them and where in the sample they are located. Nuclear reaction analysis and particle-induced gamma-ray emission use high-energy ion beams to penetrate the samples, causing the atomic nuclei to combine and then break down in a different combination. In the process, the nuclei emit gamma radiation or other ionizing radiation, such as protons and alpha particles, whose characteristic energies can again reveal the elements which produce them. This technique is particularly effective for identifying lighter elements and can also reveal how sample compositions change at different depths. Many other methods are also available, including elastic recoil detection, particularly useful for measuring concentrations of hydrogen in materials, and secondary ion mass spectrometry, used to detect ions with widely ranging masses, from single protons to heavy protein molecules. Together, they make ion beams a powerful tool for sample analysis, benefiting fields as wide-ranging as art history, electronics, forensics, biomedicine, and astronomy. In one study, PIXI was used to determine the composition of a pigment used in a painting thought to be attributed to Leonardo da Vinci, a claim which has long been disputed by art historians. The X-rays produced in this analysis revealed high levels of copper in the white paint used in the picture. Since traces of copper were commonly found in white paint from Renaissance-era Italy, this signature was a key element in helping researchers to pinpoint the location and time period of the painting's origin. Therefore, PIXI provided crucial new evidence that Da Vinci could well have painted the artwork. In another study, PIXI was used to distinguish between different types of gunshot residue, which is composed of particles just a few micrometers across. In a combination with the technique of scanning electron microscopy, or SEM, PIXI clearly revealed the presence of several metallic components which can be classified as gunshot residue. Since the amounts of these compounds will vary between different types of residue, the higher sensitivity of PIXI compared to SEM could make it a more reliable tool for determining gunshot residue in difficult forensic samples. Finally, after one of the Hubble Space Telescope's cameras was brought back to Earth in 2009, PIXI was used to study the compositions of the materials which had impacted it over its lifetime. Again, in combination with SEM, the technique revealed that most of the impacting objects were tiny particles of a rock named micrometeoroids and contained high levels of metals like aluminium, iron and nickel. This gave astronomers new insights into the elusive objects inhabiting the expanse above Earth's atmosphere.